Thank you so much. And let me read a few words because I'm not used to this format yet. I'm honored to have this opportunity to address the courageous young students and their teachers in Ukraine, in the proud but beleaguered nation of Ukraine. I myself was a teacher for most of my life. I taught at Stanford and Berkeley and Boston University, MIT, and Harvard. And I shared a Nobel Prize in 1979 with Steven Weinberg, with whom I went to high school and college, and with the Pakistani physicist Abdus Salam. Today, I'm retired. I don't teach anymore, but I am the editor of a magazine called The Inference Review, which I would like to advertise. So you can, it is free, it's available on the internet, and I don't know if you can see this. You should be able to see this. Good.
Yeah, we can see.
InferenceReview.com. We just have an interesting article on the remarkable experiments that was just reported, which seem to violate the predictions of the so-called standard model of physics. Let me begin by telling you two tenuous ways in which my life is related to Ukraine. Very tenuous. My name, to begin with, Glashow. Glashow arises from my father's name. My father immigrated from Belarus a long time ago in 1905, and his name when he came was Gluchovsky. Now, Gluchovsky comes, it turns out that my father's grandfather, after many years in the Tsar's army, he was born in Gluchov. Gluchov is a town in rather near the Russian border in Ukraine, and that is how my name came about. He was spent years with the Tsar's army, as a result of which he was awarded the baths in the city of Bobruisk. He became the manager of the baths, which became known as the Banya Gluchovskaya, and that was where my father was born, in the town of Bobruisk in Belarus. Anyway, that's one way in which the baths were there until the Nazis came, and I think they were destroyed. My second connection to Ukraine is due to the great astrophysicist, whom I never met personally, George Gamow. George Gamow did many wonderful things, and he wrote an early paper, which is famous because it was written by Alpha, Beta, and Gamow. It sounds like Alpha, Beta, Gamma, but these are the names of three different physicists. And that paper was on the origin of the chemical elements, which he worked on. He also wrote books for children, and among those books were a trilogy of books called Mr. Tompkins in Wonderland, which I read when I was a kid, and a book called 1, 2, 3, Infinity, which was published in 1947 when I was just 15 years old. And it was from that book, written by an Ukrainian who was born in Odessa and educated in Ukraine and also in Leningrad. It was from that book that I first learned about neutrinos. And that brings us to the subject of my talk, which are neutrinos. So they're my favorite particles because they were explained to me by Gamow to be thieves of energy, and I will explain that later on. Let me now approach the subject of neutrinos chronologically. neutrinos have a great deal to do with radioactivity, so I have to start with the discovery of radioactivity, which was by a French scientist called Henri Becquerel, and he discovered radioactivity in 1896. Very soon thereafter, the Curies, Madame Curie and her husband, Pierre, discovered two exceedingly radioactive elements, much more radioactive than the uranium that Becquerel worked with. They discovered radium and polonium. Then what happened next, is Rutherford, another physicist, realized experimentally that there are three different kinds of radioactivity. And again, they're called alpha, beta, and gamma, just like the authors to the wonderful article about the origin to the chemical elements. Alpha radiation, beta radiation, and gamma radiation. I shall not explain what they are right now because the focus is on beta decay and beta radiation. This is a kind of radioactivity where a proton, where a neutron in a nucleus changes into a proton, producing an electron, and today we know a neutrino, actually, an anti-neutrino. Well, Mr. Chadwick in England in 1914 studied this process of beta decay, in which a neutron changes into a proton, and noticed that the electron that comes out sometimes has a little bit of energy and sometimes has a lot of energy. That is to say, technically, it has a continuous spectrum. And the question is, why does it sometimes have a little energy and sometimes a lot of energy? And it seemed that the law of conservation of energy, one of the most sacred laws of physics, was violated. In fact, two sacred laws of physics, the laws of conservation of energy and the laws of conservation of momentum, three of them, and the law of conservation of angular momentum were all violated. Did this mean we had to give up these laws? Well, one famous, very famous physicist, one that I actually met and ate with on many occasions, it was Niels Bohr. Niels Bohr was one of the founders of quantum mechanics. And he was really upset by these experiments, so much so that he was willing to abandon the law of conservation of energy. And he wrote a paper inventing a theory, quite false theory, which violated conservation of energy. Now, that was in 1924. Then we come to 1930. And in 1930, there was a conference in December in Germany, in Tübingen. And a very famous Swiss physicist, Wolfgang Pauli, was invited to that meeting. But he chose not to attend the meeting because it conflicted with a Christmas ball, which was to be held in Zurich. And he preferred dancing to going to physics conferences. So he wrote a letter to his friends at the conference. And the letter began, it was a conference on radioactivity. So he began the letter, "Dear radioactive ladies and gentlemen." The lady was, of course, Madame Curie, who was present at that meeting. "Dear radioactive ladies and gentlemen, I have hit upon a desperate remedy." And then he explains, "In the nuclei, there could exist electrically neutral particles, which I will call neutrons." Now, the real neutron had not yet been discovered, so he was using this word that was not used before. These neutrons would have a mass no greater than 1% of the mass of the proton. The continuous beta spectrum the thing I was talking about that was plaguing everybody, would then make sense if in beta decay, in addition to the electron, a neutron is emitted. Today, we would not say that. We'd say an electron and an antineutrino is produced, such that the sum of the energies of the electron and the neutron is constant. I admit that my remedy may seem improbable, but nothing ventured, nothing gained. Thus, dear radioactive people, scrutinize and judge. Unfortunately, I cannot appear personally at the meeting since I am indispensable in Zurich to go to the dance. In 1932, this same physicist Chadwick, who discovered the problem in the first place, discovers the real neutron. The real neutron is the particle like the proton that are the constituents of all nuclei. They were long thought to be elementary particles, but as you all know, if you're studying a little physics, the neutron and proton are now known to be made of quarks, but that we'll not talk about that today. So Chadwick discovers the real neutron, and 1 year later, an Italian physicist, Enrico Fermi, creates a theory of beta decay. And in that theory, he renames the Pauli's neutron, because that was the wrong concept, as the little neutron, the neutrino. So it was this man, Fermi, who named the neutrino. And he also used antineutrinos, and he created a theory in 1933 which remained the theory of beta decay for fully 20 years, over 20 years. Now, skipping along, the neutrino was a particle that could not be observed, or at least Pauli thought it would never be seen. It was too difficult to detect. But physicists, experimental physicists, are very smart. And by 1956, experimenters at a nuclear reactor discovered the antineutrinos coming from the reactor, and they observed them. So that was a very famous discovery in 1956. About 50 years later, the one surviving member of the collaboration was given the Nobel Prize. It took 50 years before he got the Nobel Prize. Meanwhile, Pauli himself had waited, let's see, he predicted the neutrino in 1930, so he had waited 26 years for the particle that he predicted to be seen. So he wrote a telegram to the discoverers of the neutrino, and the telegram said, "Everything comes to he who knows how to wait." Then in 1960, John Updike, a poet and a novelist, wrote a poem about neutrinos. And may I read you the poem? It's called Cosmic Goal. Neutrinos, they are very small. They have no charge and have no mass and do not interact at all. The Earth is just a silly ball to them through which they simply pass, like dustmaids through a drafty hall or photons through a sheet of glass. They snub the most exquisite gas, ignore the most substantial wall, cold shoulder steel and sounding brass, insult the stallion in his stall, and scorning barriers of class, infiltrate you and me. Like tall and painless guillotines, they fall down through our heads into the grass. At night, they enter at Nepal and pierce the lover and his lass from underneath the bed. You call it wonderful. I call it crass. That was his poem. in 1960, just 4 years after neutrinos were discovered to exist. Now, many, many more things happened since, and I don't really know how much time I have, so I'll simply continue talking until the lovely young lady who is our moderator will choose to interrupt me. So the next big thing that happened is it was discovered that there's a second kind of neutrino. There was an electron neutrino, which is affiliated in some way with the electron. And there was the muon neutrino, which was associated with another particle that had been discovered in cosmic rays in 1938. It's called the muon. And hence we have an electron neutrino and a muon neutrino, and they're different from one another. This surprised a number of physicists, but not me, because my teacher, Julian Schwinger, explained to me how there had to be a second neutrino, second kind of neutrino. Now, by the way, as we sit here, there are trillions and trillions, maybe a trillion neutrinos going through our bodies in every second, and we don't notice it. Now, neutrinos were also supposed to come from the sun. And so this time neutrinos, not antineutrinos, because the sun is busy converting hydrogen into helium. That's how it makes its energy. And in the process of converting hydrogen into helium, you have to change protons into neutrons. And the only way that can happen is through the process of weak interactions, which involve neutrinos. So we knew that neutrinos were coming from the sun, and we knew how many neutrinos were coming from the sun, but we didn't see them. We couldn't see them until 1968, when a brilliant scientist from in New York managed to do an experiment at a nuclear reactor, sorry, not a nuclear, it had nothing to do with a nuclear reactor, managed to do an experiment in South Carolina, where deep in a mine, where he discovered solar neutrinos. He discovered neutrinos coming from the sun. But in addition to this good news, there was some bad news. There weren't enough neutrinos coming from the sun. According to the theories, which were pretty good, there had to be 3 times more neutrinos coming from the sun than he saw. And experimenters all over the world for years and years and years, until roughly 2000, continued to search for these missing neutrinos. That was called the solar neutrino problem, and it attracted a great deal of attention. And those neutrinos would eventually be found, and the theory would be confirmed. But that's a long, long story. We'll come back to it briefly. Neutrinos continue to be studied in many different ways. We've seen antineutrinos coming from nuclear reactors. We saw neutrinos coming from the sun. We could make beams of neutrinos, and it was through the use of neutrino beams that it was discovered that electron neutrinos are different from muon neutrinos. So all kinds of sources of neutrinos and antineutrinos were known, and all kinds of experiments were done. In 1984, we saw neutrinos coming from a supernova. A supernova is a star that explodes violently, and there were many supernovas observed in historical times, but the first one seen in our galaxy for 300 years was seen in 1984 in the southern hemisphere. And that superneutrino produced a burst of neutrinos lasting for 15 seconds or so. And those neutrinos were seen by experiments in 3 different continents: in Russia, in Asian Russia. I'm not sure whether it was Europe or Asia. It was seen in Russia, it was seen in Japan, they were seen in Japan, and they were seen in the United States. So the observations of neutrinos have been seen coming from two different stars. One is the supernova 1984, the other is our dear sun. Skipping along, in 1998, I was at a conference in a lovely city, the city of Takayama in Japan, where an important physics conference was being held. And at that physics conference, the Japanese experimenters announced the discovery of what are called atmospheric neutrino oscillations. Another source of neutrinos had been discovered, neutrinos that are produced by cosmic rays that strike atoms in our upper atmosphere. And this experiment proved in a complicated manner that neutrinos have mass, that they must carry mass. They could not be massless particles. And this was an astonishing discovery. It was not predicted by the standard model, the otherwise successful standard model of particle physics that we have. And consequently, the audience stood up and applauded. It was a standing ovation at a physics conference. Now, there have been standing ovations at operas and at musical concerts and even for speakers, but never had I seen at a physics conference a standing ovation. It was that exciting. The next such standing ovation occurred with the discovery of the Higgs boson in 2012, but that's a subject for another day. It turned out in 2000 that there were three different kinds of neutrinos, and the third kind of neutrino was observed in 2000. In 2001, in Canada, an experiment was done that found the missing neutrinos that I talked about earlier. The solar neutrino problem was solved. The solar neutrino problem was created in America. It was confirmed all over Europe and elsewhere in Japan, but it was resolved by an experiment done in Canada. So science is an extraordinarily international discipline in which all countries, Ukraine among them, make significant contributions. Finally, in a minor way to end my discussion of neutrinos, took place in 2021, and it had to do with one of my first papers, which I wrote in 1959, which was 62 years before. I had predicted that there should exist an intermediate vector boson, which was later found, of course, and that intermediate vector boson could be made by energetic neutrinos in cosmic rays. And it had to be very energetic neutrinos, and it was very difficult to see such neutrinos because there are very, very few of them. But finally, at an experiment done on the last of the 7 continents in Antarctica, at the South Pole, an experiment appropriately called Ice Cube observed a neutrino which came from the production of a W boson by a neutrino. So that resonance, that resonant phenomena that allowed that observation to be made was called the Glashow resonance for many years. And finally, an example after 62 years of the Glashow resonance was found. Not an important discovery, except to me, because how happy I am that something I predicted 62 years ago was finally found, even though it was too late for anyone to care about the discovery. Anyway, that ends my tale about neutrinos. I hope I've left a lot of time for questions. I certainly have gone over a lot of things that I'm sure you don't understand. I'd be very happy to try to explain. Thank you.
Thank you very much for your presentation. So we have a lot of questions. So the first question is from Lyubov. What do you think about the thermonuclear reactors? Do they have a future? And is it possible to build a thermonuclear reactor like Tony Stark did in Iron Man or in Marvel movie?
Wow, the story of controlled nuclear fusion is a very long story, beginning perhaps in Russia with their invention of the tokamak back in 1950 or so. Anyway, people have been trying ever since, and these days on the web, every week or so, we hear about some advance that has been made in the search for controlled thermonuclear energy. However, these advances have been very gradual. A successful example of fusion of controlled nuclear fusion was obtained in 1994, producing a small amount of energy. And that record was only beaten last year when they got about twice as much energy, which is enough to keep a light bulb going for an hour, not much more than that. So not much progress has actually been made. There are very big obstacles to controlled nuclear fusion. One problem has to do with fuel, because the fuel consists of a mixture of two of the three isotopes of hydrogen, hydrogen-2, called deuterium, and hydrogen-3, called tritium. The problem is there's lots of deuterium on Earth, but there is no tritium. Tritium has to be manufactured. So the only way, or one of the only ways in which you can successfully accomplish nuclear fusion is to have a device which simultaneously produces energy and produces fuel to make more energy. And that's a very big challenge, and a challenge which has not yet been fully addressed. So it's going to take a long time, and I would bet against controlled nuclear fusion being available anytime in this century. Beyond that, I don't know. Anything is possible.
Okay, thank you. The next question is from Anastasia. Do you think people will ever learn to perform surgery in four-dimensional space or in other superspaces?
Surgery?
Yeah, operations.
No, the extra dimensions that my friends who do string theory believe in are very tiny and unobservable, and they have no effect on us. We do surgery with lasers, so some new discoveries in physics are important for surgery. That's certainly true, but I'm afraid that the new dimensions that some people are convinced exist have no relationship at all to the medical profession. And the answer is, I could have simply said no.
Okay, the next question is from Stanislav. Can neutrinos can be used to create new super heavy chemical elements?
No. Again, no. The neutrinos, well, the story of finding super heavy elements beyond uranium is very interesting. We've up to element number 218 has all elements beyond 92 up to 100, up to 118 have been found and named. And that was how things were 5 or 10 years ago, and nothing has been found since. Neutrinos interact so weakly that it is very difficult to observe them, and it's certainly not possible to use them to find these very hard to create elements. The Russians, the Germans, and the Americans have been working very hard to find, even the Japanese, to find transuranic nuclear elements beyond uranium. And they probably will find more, but neutrinos will have nothing to do with it. Neutrinos recently have been addressed as possibly useful by the American government for the purpose of monitoring the nuclear reactors of unfriendly countries. That is to say, the Americans would like to know if the Iranians are using their reactors to make plutonium. And the question is, can you use neutrinos to make such observations from a distance? And the answer is yes, but as the distance gets bigger, it gets more and more expensive. So yes, we can build a detector 1,000 miles away, 1,000 kilometers away from an Iranian reactor, and we can tell whether that reactor is producing plutonium, but it would cost a great deal of money to do that, perhaps $1 billion, something like that, to produce the device. Nonetheless, some American scientists are working on trying to do that job less expensively. So we may use neutrinos for that purpose. Neutrinos can also be used for the purpose of Earth tomography, to study the inner structure of the Earth, and that is being done. Another particle, the muon, can be used to, and has been used once and will be used again, to search the pyramids for concealed passages within the Egyptian pyramids. And that was done back in the 1960s by a colleague of mine at Berkeley. And today, further experiments are being launched in collaboration with the Egyptian government to search for hidden passages. But these applications are the only ones I can think of. One is monitoring reactors, and the other is looking for secret passages in different parts of the Earth. Thank you.
Okay. The next question is from Mikhailo. What happens to neutrinos during a nuclear explosion?
Yes, nuclear explosions produce, of course, a great deal of fission or fusion, either one, produce lots of neutrinos, but they don't contribute to, they don't affect your health. Neutrinos are so weakly interacting that a neutrino can go through a light year of steel without interacting. The only way we can detect neutrinos is because of their immense numbers. And even with those immense numbers, we see only a few interactions. Maybe after many years of study, we have observed, let us say, a trillion neutrinos, or maybe a quadrillion neutrinos. But even if that quadrillion of neutrinos went through my eye, it wouldn't affect me in any way, whatever. So there are no health effects from nuclear weapons. However, there are lots of other effects. So let us hope and let us pray that the Russians do not decide to use them in this barbarous conflict that they have created. Thank you.
We hope as well. So the next question is from Maria. What is your next biggest expectation concerning neutrinos?
Concerning neutrinos?
Yeah.
Yes, well, well, let me first say that the study of neutrinos is very actively being pursued today in many countries and in many, in Japan, in America, in Canada, in Russia, elsewhere. In America, there's a series of very large experiments that are being carried out or planned at Fermilab. Fermilab is near Chicago. It's the location of what was once the world's most powerful accelerator, is no longer, but the accelerator will produce the world's most powerful beam of neutrinos, and that will be used for a number of purposes. There are a number of unresolved questions. First of all, is to measure their masses. We know a great deal about their masses from astronomical observations and also experiments on Earth. We know that their masses are very small. We know a great deal about the differences of the mass differences. The absolute scale of their mass is not yet known, and we hope that that will be learned, if not by accelerators, then by astrophysical measurements. Secondly, there are details about the mass spectrum that remain. We don't know which neutrino is the heaviest and which is the lightest. That must be determined. And we don't know whether there are just 3 neutrinos or possibly more. We know, and we've known for 50 years, that there are only 3 active neutrinos that play a role in a significant role in nature, but there may be additional neutrinos, and they're called sterile neutrinos because they don't have any effects, or actually their effects are so small as to be negligible ordinarily. So people are searching for that, and people are searching for a flaw in our theoretical description of neutrinos. So all that is going on today at experiments being done now at Fermilab and being done in the future there in Japan and elsewhere. So there will be news about neutrinos in the future. I've indicated that there has been news about neutrinos since their discovery in 1956 until now. In fact, it was just a few years ago, I think 3 years ago, that a third source of neutrinos was identified in the sky. It was a blazar, and it was again the experiment at the South Pole that observed a neutrino coming through the ice at the very same moment that photons and X-rays were being observed from the same event in the sky, a so-called blazar. So that was happening just in 2017. Events are taking place all the time. Another coincident, what's called multi-messenger event, would be to see a high-energy neutrino at the same time that we see a gravitational wave. So there's a new kind of astronomy that has developed, gravitational wave astronomy, and the intersection between gravitational wave astronomy and neutrino astronomy might be very interesting in the future.
Okay, the next question is from Stanislav. Can neutrinos accelerate absolutely any particles? Are there any limitations?
Can they accelerate
any particle?
They travel at virtually the speed of light, and usually they do nothing at all. When a neutrino from the sun strikes the nucleus of an atom in a detector, it will cause the atom, it will produce ionization. It will the neutrino will interact with the nucleus by the process of inverse beta decay, producing an electron or a positron. And we can see that electron or positron in a detector. The process is a simple one. The neutrino hits an atom, produces an electron. The electron produces light, and the light is seen by the detectors. But it doesn't accelerate anything. It just disappears and is converted into an electron or a muon in the course of interacting. It doesn't do very much of anything. And the neutrinos seen from the sun have very low energy, just a few million electron volts, whereas the electrons that come from cosmic rays have millions upon millions of electrons, a million or a billion electron volts.
Okay, the next question is from Diana. Do you think that the standard model or its daughter series can combine all interactions, including gravitational ones? That is, can it claim the role of the theory of everything?
Okay, well, first, before we worry about a theory of everything, let's worry about the standard model, because we have not confirmed the truth of the standard model. Just a few days ago, on the 7th of April, an announcement was made by the scientists at Fermilab, who have analyzed the results to 10 years of experiments at the Fermilab accelerator. The accelerator is now not operating, the collider, but it operated for many, many years and collected a huge number, actually 4 million events of which were the production and decay of W bosons, which are the carriers of the weak force. So they saw 4 million Ws, and they carried out with this historical data, making use of this historical data, they studied the mass of the W particle, and they made the most precise observation or determination of its mass that has ever been done. And that result turns out to be in stark disagreement with the predictions of the standard model. So the big question, but that's an astonishing result, and that the confidence level is very high of that departure from the standard model. It's alleged to be 7 standard deviations, and that's well beyond the accuracy necessary to make a convincing discovery. So that is such an extraordinary observation that it demands extraordinary proof. In fact, it was Jean-Louis Laplace in 1810 who said that extraordinary discoveries require extraordinary proofs. And so we have to wait for a proof of this result before we abandon or alter or change the standard model, which does not include gravity. Now, as far as including gravity goes, first of all, the question is, does that really, would that really give us a theory of everything? No, of course not. It would not explain, it's not a cure for cancer. It does not explain why there exist rabbits. It does not tell us the origin of life on Earth. It is certainly not a theory of everything. It would be a theory of gravity, yes. We may have such a theory in the form of string theory, but for reasons that I don't want to go into detail, string theory is not all that it's cut out to be. When string theory was created in many years ago, decades ago, about 30 years ago, it was hoped that string theory would answer many of the questions we have, like why are there three different leptons, three different neutrinos? Why are there 6 kinds of quarks? Why this, why that? But it didn't answer any of those questions. And in fact, today, string theorists believe that questions like that cannot be answered because they are accidents of nature, because there exist zillions and zillions of different universes, and the answers are different on each of those universes. And we just happen to live in the universe we live in, so that we cannot address these questions. So questions that were once the most interesting are now questions we cannot answer. That's what string theorists say, but I don't believe them. Okay.
The next question is from Katerina. What does the increase of neutrinos tell us about events in space? And what we can learn about stars or any other objects in space using neutrinos?
Yes, that's, we're just, neutrino, I had a very good friend in Italy, a female physicist, experimental physicist, who, Mila Barbaro-Cialin, she organized a series of conferences every 2 years in the beautiful city of Venice. And I had the great pleasure to attend those conferences, some of them, 3 of them. Unfortunately, she's died, but the conference still takes place every few years. The series of conferences called Neutrino Astronomy, and that was a subject that she introduced long before it existed. Today, neutrino astronomy does exist. We've seen neutrinos coming from a supernova. We've seen many neutrinos coming from the sun. We've seen neutrinos coming from a blazar. And the hope is that we will see neutrinos in association with other particles. They will be a part of what is called multi-messenger astronomy, which will involve neutrinos and electromagnetic radiation and other forms of cosmic rays and gravitational waves. So all of these forms of observation will be linked to one another in this new science of multi-messenger astronomy. And there are many things we can learn, and we are learning. The most exciting discoveries today are that, of course, have to do with the discovery of gravitational waves by the LIGO laboratory, which is a system today consisting of 4 different detectors, 2 in the United States, 1 in Italy, and 1 in India. And the one in India doesn't exist yet, and 1 in Japan. 1 in Japan and 2 in America, and an Indian one to be completed, and others in other countries. And these facilities are making fantastic discoveries with considerable frequency. And I have a very good friend who works at these, and he tells me about the kinds of discoveries they make. They will measure cosmological parameters. They will use gravitational waves from distant supernovas to learn something about the evolution of stars and galaxies. It's a very powerful new tool, even more powerful when used in collaboration with other forms of astronomy. So today, the astrophysical frontier is exciting, very exciting. even more exciting than the elementary particle frontier. So the answer is yes, I'm watching the skies. That is to say, I'm watching the internet to discover what my friends are finding all over the world in the heavens above.
Okay, the next question is from Sophia. What do you think about cold fusion? Do you think this is unscientific?
What, about what?
Cold fusion. Fusion, maybe. F-U-S-I-O-N.
Fusion?
Yeah, yeah.
About nuclear fusion?
Cold fusion.
Oh, cold fusion. Oh, nonsense. The original experiment were, if not fraudulent, certainly wrong and misguided and could not be replicated. That's the way it is with strange observations. If you make an astonishing observation, it has to be repeatable. And all of the so-called observations of cold fusion have proven to be unrepeatable. They are not only unrepeatable, but they are incompatible with the laws of physics as currently understood. In fact, if the original cold fusion experiments had been correct, they would have produced so many neutrons that it would have killed the experimenters. No, the experiments on cold fusion, which occur again and again and again, are consistently wrong, misguided, or fake.
Okay.
Sorry about that.
The next question is from Stanislav. Please tell us about your prediction of C quark.
Of my prediction of what?
C quark.
I didn't predict any. Oh, the C quark. Oh, yes.
Yeah, yeah.
Yeah, that's true. Way back in 1964, a colleague of mine, James Bjorkane, and I were living in Copenhagen, in Denmark, and we imagined, we noticed that Murray Gell-Mann and others had invented quarks, and that was in January of 1964, maybe a little earlier by others. But anyway, there were three of them, the up, the down, and the strange quarks. And at the time, we knew that there were four leptons. I mean, nature consists of two kinds of what we call matter particles. Leptons, which are electrons, are an example, and quarks, such as the up and down and strange quark that Gell-Mann introduced. So there were three quarks, but there were four leptons. And the leptons formed two doublets, electron and one neutrino, and muon and the other neutrino. But the quarks formed only one doublet, the up quark and the down quark, and the strange quark was all alone. So if there were to be symmetry in nature, there would have to be four leptons and four quarks. And for that reason, we invented the fourth quark and called it the charmed quark. And years later, working with my collaborators, Iliopoulos and Mayani, we realized that there had to be a fourth quark, that the theory of weak interactions would not make sense without a fourth quark, and the unification of weak and electromagnetic interactions that I had suggested in my thesis could not take place without the fourth quark. So it was very exciting to have done that, and we did predict the C quark, but then we were surprised again by the discovery that there were two more quarks. First the B quark, and then the Japanese theorists were very smart and said if there's a third quark, there has to be a fourth quark. And their argument was a little bit more profound than mine with James Bjorkane, but the fourth quark did exist, and early in this century, it was discovered. It was the last great discovery. I think it was in 1997 that the top quark was discovered at Fermilab. Are there any other quarks? That's a big question. It's not clear. So far, there's no indication of any additional quarks, and there's absolute certainty that there are no more active neutrinos. So if there are other quarks, their neutrinos, if they have neutrinos, have to be very heavy. And we'll see whether they exist or not in the future, perhaps.
The next question is from Diana. Do you think that particles of new physics can interact even less than neutrinos will also be discovered?
Yes, that's a good question. It is certainly possible that such unobserved particles exist. They have been searched for. It's still thought that the mysterious dark matter of the universe, if indeed it exists, is in the form of particles. And people have looked for these particles with consistently no results. They haven't found these particles. My colleague and friend, Frank Wilczek, has suggested the existence of particles called axions, which are very weakly interacting and which may actually constitute the dark matter of the universe. And they are being looked for actively by people at many different locations, but nobody has discovered those particles as yet. So there are many possibilities for extremely light particles that have not yet been discovered, and even for extremely heavy particles that have not yet been discovered. But experiments will continue, and perhaps more particles will be found in cosmic rays by dedicated experiments at accelerators, in deep mines, all kinds of places under the water, under the ice, under the land. We look for particles in such obscure places in order to get rid of the background produced by the cosmic rays that are a background to experiments unless we go deep underground. So that's the reason we are now doing lots of interesting experiments underwater, deep under ice, and deep under the land in many different countries.
Okay, the next question is perspective. Are there possibilities to organize research projects so large that they unite the participation or implementation of almost all countries, which could contribute to deep cooperation and unity? For example, something similar to the Hadron Collider or even larger project.
Well, yes. I believe that Ukraine has been an active collaborator at CERN for many years, and which involves many, many countries, as if not as members, as observers. My country too is affiliated with CERN, but is not a member of CERN. Nonetheless, we do experiments there, and such laboratories as CERN are open to scientists from any country in the world, without exception. And will there be future laboratories of that kind that are open to everyone? It's not clear. The Chinese have built some wonderful facilities, including the world's largest radio telescope, which was recently deployed, but it is not openly available to scientists from throughout the world. I think they've devoted, in principle, a small percentage of the time available to observers from other countries, but not any other countries, just countries that they decide are appropriate. In the past, there has been considerable cooperation between the United States and Russia. Even in times of the Cold War, there was such collaboration. In fact, there was an important experiment, a neutrino experiment carried out I'm not sure if it was in Russia or Ukraine, which was called the Soviet-American neutrino experiment. That kind of collaboration hopefully will continue in the future, but not now and not for the indefinite future. That is, as far as Russia is concerned, it has counted itself out of the world community by the actions it is currently carrying out. So I don't know about that country. Of course, Ukraine will continue to be an active participant in American experiments, as it has been in the past, and in Japanese experiments, and in experiments anywhere in the world, in principle. Some countries like India have not been active proponents of fundamental physics within their country, but they certainly have been active as participants in science done elsewhere. In fact, there's an Indian physicist named Sarkar, excuse me, at Oxford, who has just written a paper for my magazine, For Inference, claiming that there is no such thing as dark energy, that the accelerated expansion of the universe that we've been discussing for many years is a fiction and is wrong. And he has reason to think that the universe is not as isotropic as had been thought, and that the evidence for dark energy is wrong. Is he right or is he wrong? I don't know. But there are interesting things are going on today, and sometimes they're done by physicists from any number of different countries throughout the world, including Ukraine.
Okay, this question is, what is the benefit to humanity from neutrino discovery?
There has been no definite, useful result from the discovery of neutrinos, and there has been no consequence to the understanding of the structure of strange particles containing strange quarks. That's the third quark. It's thoroughly useless, as is the fourth quark, the fifth quark, and the sixth quark. What we have learned about nature is important because it is our duty to understand, or to try to understand, the universe we have been born to. And those of us who participate in this game do it for the need to know rather than the desire to cure cancer, prevent war, or understanding the origin of life. It is an enterprise which one might say is important to the soul, but not the body.
And the next question is, could you please tell us about Einstein in your background, in your
Einstein,
room?
what?
No. Could you please tell us about Albert Einstein in the background of your room?
Oh, that. I always have Einstein looking over my shoulder. That was a gift to me. It is, in fact, a chair. It is an Einstein chair. And it was given to me by my wife, maybe 30 years ago. And it's been sitting there with Einstein looking over my shoulder ever since. Einstein is certainly one of my great heroes. And I just read a wonderful book, fiction, about Einstein. As you all know, Einstein had a daughter, Liesel, before he was married to his first wife. And that child was lost to history. We don't know what happened to Einstein's first child. He had two more children who were boys, but Liesel disappeared from history. And so my friend, who's also a physicist, has written a book called Unification, where it turns out in this fictional book that Einstein's daughter lived, and she was adopted by some Russians. She was born in Serbia, but was adopted by Russians. And then she grew up and she married a famous biologist, but that biologist was sent to the Gulag in Russia because he did not believe Lysenko's science. And as you know, in Soviet times, biology was controlled by this imbecile called Lysenko. And so she suffered for many years until she was brought back when it was realized that she might be the child of Einstein. They realized, the Soviets did, that they could use her as a spy to try to attract Einstein toward the communist sentiments, to become a supporter of the Soviet regime. So they brought her back to England, and meanwhile she had a daughter. Einstein's daughter had a daughter as well, Bella, who was kept in Leningrad during the siege of Leningrad, but she survived that. Anyway, it's a fiction which goes on, and it's a very interesting story, which is not true, but it could have been true. And I mention it only because I just read the book. And in that book, Einstein discovers this unified theory that he was searching for most of his life, but he does not publish it because he feels that the people of the world are not yet prepared to have such a beautiful theory. So it's curious. It's a curious book. Interactions, and it's by a man named Ron Rubin, and it does not yet exist as a book, but I will let you know when the book exists.
Thank you. And maybe the last question, what is your motivation to do science?
Motivation for what?
To do science overall, to do research.
Well, when I was small, I got interested in science fiction. I read a great deal of science fiction. And that led me to science. And by the time I was 15, I was already reading books like this book by George Gamow, the Ukrainian scientist that I mentioned before. So I remember being at a department store in New York with my mother, and I insisted we go to the book department. I saw this book that had just been published, and it cost $3.75, which in those days was a lot of money. So I told my mother I want to buy the book, and she said it's very expensive. And I said, no, I want to buy it. So I bought it, and that's where I got interested, learned things about particle physics. There weren't very many particles in those days. There were just protons, neutrons, electrons, neutrinos, and muons. But it was enough to get me fascinated. Let me say I was addicted to science at the age of 15. Now I have documental proof because I know the book was published, first published in 1947, and that's when I bought it, and that's when I got interested in becoming a theoretical physicist. So by the time I was in high school, which was then, I was committed to becoming a theoretical physicist. And in fact, I went to, many members of my class at high school became theoretical physicists. And the same was true in my class at Cornell University. Throughout high school and throughout college, I knew that I would become a theoretical physicist, which indeed I did. And I'm very happy I did so.
Thank you very much for your presentation and for your motivational speech and for your answers for all questions. I'm very grateful for your efforts and time you gave us.
And I hope that my friends in Ukraine and my friends who have been forced to leave Ukraine will have a peaceful future in a great country.
Thank you very much.
Independent Ukraine.
Thank you very much. We hope it will be as well. Thank you. And maybe we will invite you to Kiev sometime.
I would love to come to Kiev.
After our victory. Шановні учасники, всім дякую за лекцію та ваші питання. Чекаємо вас на наступній лекції. Будь ласка, реєструйтесь. Запис лекції ви можете переглянути на каналі YouTube. Thank you very much and goodbye.
Thank you and goodbye.
Goodbye.